So I briefly mentioned this problem on the first day, but this talk is mainly it's a survey. But maybe at the end I'll give you some ideas of possible directions that I have. Yeah, so let's get started. So for those of you who was not here on the first day, let me just briefly define what the t-perfect graphs are. So you are given a graph, and this f dash step of g is defined as the following. So basically this is for formulating the stable set problem for this graph G. So for each edge, you're allowed to pick at most one of these two ends, and variables are binary. So if you collect the set of 0, 1 vectors satisfying these constraints, they will correspond to the stable set in this graph G. So basically, this is just the stable set. That's why I just use this step notation. This step, this f dash the f step of g is a relaxation of this set, which is sometimes called the stable set polytope of a graph. These are not equal, but sometimes this relaxation is too weak to use. So the one way to strengthen this relaxation is to add some other valid inequalities. So one of the most kind of important class of valid inequalities is this. So basically, for each cycle, we know that stable set contains strictly less than half the vertices. So this inequality just kind of captures that. And after adding these inequalities, I'm gonna denote the resulting set as T step of G. Okay. So by definition, we know that step of G is contained in F step of G. But I have this is higher than F step of G, but this is still a relaxation of this stable set polytope. Okay.
Where does SPP lie? What's there?
I think for theta body you are adding clique inequalities.
No. So I think it captures this for the maybe so.
Oh, you mean theta body might be stronger than this one? This T step of G? I'm not sure. Okay. Maybe theta body might be contained in this set. Not sure.
Yeah. And I think my question is like whether like being T perfect implies being perfect.
Oh. So the answer is no actually. So on odd cycle, I'm gonna tell you a little bit, but perfection and T perfection are not equivalent. I mean, one thing does not imply another. They are kind of incomparable. If something is perfect, something is not T perfect. No, they're not comparable. No. You don't have an auto, but odd cycle. You could have triangles too. They are incomparable. If you have any questions, you can always interrupt me. Okay. Yeah. So you say the graph is T perfect. As I said, if these two sets are equivalent. Okay. Okay. I will maybe. Okay. So let's see some examples of T perfect graphs. mark. So every bipartite graph is T-perfect. That's because if a graph is bipartite, then f step of g is equal to the stable set point. Okay. And then second, every odd cycle is T-perfect. If you just have one odd cycle, then that's T-perfect. But that's not perfect, right? Because that could be an odd hole of length greater than 3. Yeah, T-step is, so F-step is a polytope. So T-step itself is contained in F-step of G, so it should be polytope.
But then that is just a
This is, you take the convex hull of the point, then you get the polytope. So you need to argue that if you have just one odd cycle, this set is equal to stable G, but that's not difficult. Okay. Because you're just adding one inequality to this formulation. You can actually prove that if a graph contains at most one odd cycle, it is T-perfect. So it's a nice exercise for graduate students taking combinatorial optimization. But actually, you can kind of push this number to 3. Okay, with a little bit of argument. So the smallest non-T-perfect graph is actually K4. So K4 is not T-perfect. So K4 contains 4 triangles. This is the smallest example not containing more than 3 cycles. Somebody asked why this is not T-perfect, so let me give you a short proof of it. So a step of G, a step of K4 is, if you look at its stable sets, so they are either empty set or just singletons. So if you take the convex hull of them, it's just a simplex. So this is basically defined by, you have 0, 1 inequalities and also x1 plus x4 at most 1. So this is just a simplex and stable stable. Okay. But if you look at T step of G, step of K4, it's defined by these 2 types of inequalities and also triangle inequalities. The triangle inequality will be like x1, x2, x3 less than or equals to 1. So because triangle inequality has 3 variables in that, so we can argue that 1/3 everywhere point is contained in this set. But this point violates this inequality, right? If you sum up these, you get 4/3, which is greater than 1. So this point is not contained in step of G. So that's why so then these 2 are not equal, so K4 is not the perfect. So people use this, I think this in French word, it says true. Is it like odd or cycle? I don't know. True. Oh, maybe that's why. I don't actually know. So in the so Kvatar. Yeah, so the mean
And what is it?
f is fractional. So it just this is kind of like a textbook formulation, and this is a p. So
So you may want to just mention that perfect is the definition of perfect is also critical for students.
oh yeah, okay. Yeah. So okay. So now theorem. This was the conjecture of Kvatar by Kvatar, 1975. So like K4 is not T perfect, right? So I wanted to mention maybe here remark. So vertex deletion preserves T perfection. So which means that if you have a T perfect graph, then every induced subgraph is also T perfect. So if your graph contains K4 as an induced subgraph, it means that the graph is not T perfect. Edge deletion doesn't preserve T perfection, unfortunately. That's why it's not a minor closed family. And a subdivision, I'm guessing most of you already know this, but let me just define it. Is what is obtained from K4 after replacing each edge of K4 by a path. Okay. So basically, you have K4. Now you are kind of subdividing these edges. Okay. So we know that if the T-perfect graph does not contain K4 as an induced subgraph. So conjecture by Kvatar was as follows. So if a graph contains no K4 subdivision, that's just a subgraph, not as an induced subgraph. No K4 subdivision, then it is T perfect. Okay. Like this result is proved in 3 different papers, and 3 different like one of these 3 was coming from a completely different community. That's because this polytope T sub of G is kind of natural in many settings. You can obtain this. You can look at this polytope from integer programming, maybe from computer science, or from other areas too. So the first paper that appeared, first paper containing that polytope is the paper by Kvatar, I think. But I'm guessing many people already looked at that polytope before, or not. So they just didn't write any result.
The one showing that shows imperfect?
No, I think people started calling it as T perfect later. I think Kvatar himself didn't name it. So this paper, the same paper, actually considered perfect graphs. So just as a side remark, let me just give you the definition of perfect graphs. Okay. So a graph is perfect if, let me define Q step. Okay, if step of G equals Q step of G. So Q step where Q step of G is F step of G. So for each maximal click, you know that there's at most one vertex contained in a stable set. That's you're just adding them. So for each click, you take at most one vertex. So this is a polytope definition of T perfect. So another a graph-theoretic definition is that for every induced subgraph, the click number equals to the chromatic number for every induced subgraph. Well, this is the polytope definition of perfect graphs. So this paper by Bata contained this definition here, Q step of G and T step of G. But I think people named these graphs as perfect or T perfect much later, I think. So the reason why I got interested in this question is that we are looking at the integrality of this polytope. So we know that step of G is the convex hull of 0, 1 point. So every extreme point is binary. But this polytope could have some fractional vertices. But I'm interested in when this polytope has integral vertices. That's how I kind of got into this question. Okay. But for you guys, because it's coming from graphs, there should be like graph theoretic definitions or characterization. So I'm guessing it might be more interesting to you. So this is the first kind of large class of T-perfect graphs. There are actually more larger classes of T-perfect graphs. So K4 subdivision is odd if each path has odd length. No, each cycle has odd length. So basically, K4 subdivision has four cycles. 1, 2, 3, and 4. You call this K4 subdivision as an odd K4 subdivision if each of these four cycles has odd lengths. Okay. And this is proved by Gerard and Scriber in the 80s that no odd K4 subdivision, and this is T perfect. It's a subgraph. Yeah, subgraph. I think this is very much graph theoretic, so. But this one is minor closed family, I think. Yeah, this is odd K per minor. Yeah, odd minor. Okay. So I think it uses some arguments.
It uses the sequence conversion theorem for regular matrix.
He uses some like the tools from binary matrix, but I think they don't really.
There's a structure theorem for
So actually, it's not that every odd K4 subdivision is not T-perfect. Some odd K4 subdivisions are T-perfect actually. So let's say if you subdivide your K4 this way, then you get a T-perfect graph. So you just keep a pair of vertices showing edges, and then you just start. You subdivide the other 4 edges with even length path, like this. And because these 2 are even, and this is length 1, so this cycle has odd length. Similarly, this has an odd length, and this is also even, odd, so this is odd. So this is an odd K4 subdivision. Well, actually, this is the only kind of odd K4 subdivision that is T-perfect. So, theorem. Francisco Barahona. Shoot. 94. So, an odd K4 subdivision is T-perfect if and only if it is of the form star. Okay. And another definition on odd K4 subdivision.
So when you say it's also form, you mean
This kind, only this kind.
are you talking about the parity or?
You just keep a pair of vertices showing edges, and then you don't subdivide these 2 edges, but you only subdivide the other 4 edges.
Okay, then you are allowed to have more subdivision.
Yeah. As long as you have even number of edges in each side.
So keep 2 edges from the perfect matching.
Perfect matching.
And then you subdivide 100 times.
Yeah, so that you can get even length path for each side. So bad. If it is not star. Equivalently, an odd K4 subdivision is bad if it's not T-perfect. Okay. So the natural question is that if we exclude just bad K4 subdivisions, then can you obtain T-perfect graphs? That's actually proved recently. Okay, theorem. This is by Scriber. No, this is due to Bert Gerard and Bruce Shepard. 98. No bad K4 subdivision. Implies T-perfection. Okay. So I would say this is the largest known class of T-perfect graphs. So there's a characterization of when a claw-free graph is T-perfect, but that's kind of a small class. I'll say this is the largest class. Maybe the next question is that are there kind of other classes of T-perfect graphs, or is this the kind of largest class, and there are some other sporadic classes of T-perfect graphs. But I'm not aware of any result. But yeah. So this vertex deletion is one T-perfection preserving property of operation. There's another operation which is called T-minor operation, but that's kind of weird. And then you can define a minor operation based on those two. So another line of research is whether is to characterize these forbidden T minors, but there are not many kind of known results in that line. Converse. Oh, yeah, there are some examples like okay, one example is okay. If you don't have this set, this is an odd K4 subdivision, and this is not T-perfect. But if you add this set, this becomes T-perfect. So this graph contains a bad K4 subdivision, but this is T-perfect. So this kind of says that this T-perfection is not preserved under H deletions. So, you can subdivide the edges, but this is not T-perfect for now. Yeah, but I think the definition is defined based on polytopes, but the arguments are more or less graph-theoretic. So how do you prove something is integral polytope? You just need to exhibit an optimal solution for every linear objective. You need to exhibit an optimal solution whose optimal value is integral. So you need to kind of exhibit some sort of fractional stable set that has integral value. But when you construct this fractional stable set, you need to kind of look at the structures of these graphs. I'll say that's the kind of general idea. Okay, other question? Okay. So this is more or less the kind of structural side of T-perfect graphs. Let me move on to algorithmic side of this graph.
Perfect graphs will study the lab of minimally perfect graphs.
Yeah. So that minimality notion should be defined on some sort of this T-perfection preserving operations. There's one, this vertex deletion, and also there's another notion of T minors. People look at minimally T imperfect graphs in terms of these T minor operations, but there are actually many known examples of minimally T imperfect graphs. There are some kind of infinite classes that can be kind of nicely characterized, but there are some other sporadic classes too. Yeah, perfect. You have just two classes of infinite families, but maybe this is not as simple as perfect graphs. Okay, the theorem. So another motivation of why we study this graphs is algorithmic. Basically, one can, so given a graph, given a T perfect graph G and vertex weight, one can find max weight stable set in polytope. Okay, and then the proof doesn't really rely on the structures of T-perfect graphs. Actually, it has 3 steps. So separation over the T step of G can be done in polytope. By separation, I mean that so given a vector x, and you want to determine whether that point is contained in this set or not. That can be done in polynomial. So if there's a kind of small number of inequalities defining this set, then the question is obviously easy. Okay, so by separation, I mean given x bar in RV, decide whether x bar is contained in T step of G. Okay. So the problem is you have exponentially many inequalities because you have exponentially many odd cycles, but you can kind of separate over this polytope easily. There's an algorithm for that, and by the equivalence between optimization and separation, one can optimize a linear function, the linear function wx over T step of G. And the last step is the only place where you use this T perfection. So because T step of G is equal to step of G, there's an optimal solution of this linear function at an extreme point of this stable set polytope, which will be a 0, 1 point corresponding to a stable set. So there will be a maximum weight stable set of this graph. Yeah. Polynomial in this vector? No, this is T step. Oh, Q step. That is not known. I think that might be NP hard. But Q step is not equal to the SDP relaxation.
Yeah, Q step is not.
Yeah. So you can test whether something is contained in the smaller set of Q step. What? I don't. Or maybe that's NP hard. I don't know.
Q step because like in general you gotta solve the limit.
Yeah. Yeah.
Find the violation.
Okay. Any other question? So that's not known. So yeah, people conjecture that it can be done in polynomial time. But So every non-class can be recognized in polynomial type, but not in general. So this part, this equivalence, uses the ellipsoid method. So this algorithm is totally geometric. So the next question is whether we can find a combinatorial algorithm for solving the stable set problem. It's still open, yeah. But there's a kind of combinatorial, but not graph-theoretic algorithm for this problem, for the unweighted case. I'm gonna show you for the rest of the talk. Okay. So yeah. So the maximum cardinality stable set in a T-perfect graph can be computed by this LP. The summation of in S, XB is at most CS, where S is a family of sets, XB non-negative, where the C is a family of edges and odd cycles. Okay. The edges have C value 1, and odd cycles have C value C minus 1 divided by 2, if this is an odd cycle C. We know that if a graph is T-perfect, this is an integral system, so this LP always returns an integral optimal solution. Now you can look at its dual. That will be minimizing CS times YS for each subset, subject to, for each vertex, you want to cover. So S in C, such that V is contained in S, YS is at least 1 for each vertex in V, and YS non-negative. Okay, so this is the dual LP of this LP. Okay. So this algorithm is basically finding an optimal solution to the primal LP. But actually, if this is integral, this dual LP is also integral. So another way of solving this problem is to solve this dual LP. So I'll show you how to kind of combinatorially solve this dual LP. And then by that, I mean, I will say this algorithm is combinatorial. Okay. But this is not graph theoretic. Okay. But you know, if you look at this LP, this is just a fractional set cover problem. If you replace this non-negativity by integrality, this is just a set cover problem. But because I relaxed the integrality by this non-negativity, this is a fractional version of the stable set problem, set cover problem. Okay. So we know that the set cover problem has a log n approximation algorithm. But I will show you that, you know, this LP admits on kind of 1 plus epsilon approximation algorithm, which is combinatorial, using the log n, kind of mimicking log n approximation for the set cover. Okay, I will describe it right now. So let C be a family of subsets. V. Yeah. So, and the set cover problem is to find a subfamily F of C covering every element in V. So I'm gonna describe on log n approximation algorithm for the set cover. I'm guessing many of you already know this algorithm, so I'm not gonna analyze the log n ratio, but let me just write what the algorithm is. So for each element in V, the remaining demand is denoted dV. So initially, dV is set to 1. So as you start covering this vertex V, you will decrease this value to 0. And for a subset S in C, the average cost rho S is defined as CS divided by summation over dV. So basically, you have the cost of this set S. So if you have like large demand in your set, so it's good to pick this set, even though the cost is large, because this kind of captures the average cost of this sets, of picking these sets. Okay. Okay. For each vertex, I'm gonna use auxiliary variables x for each vertex in V, and also I'm gonna use an auxiliary variable for each subset S. So initially this is 0. Once you start covering this vertex V, you're gonna increase this value of V. And then when you start using this subset S, you increase this value. Okay, so the algorithm is while there's a vertex with demand 1, you're gonna do the following steps. So pick S with minimum average cost. And then second thing is you set YS to 1 and you set XV to XV plus rho S. for each vertex V in S. I apologize to people who already know this, but dv is 0 for V in S. And finally, update corresponding row S and return sets in the family that you used. Okay. So this algorithm is on order of log n approximate algorithm. Theorem. Algorithm 1 is on order of log n approximate algorithm for the set cover. Yeah, there's a reason why I kind of wrote down the algorithm, although you already know this. Another theorem, algorithm 2, which I will write down in a minute, is on order of 1 plus epsilon APX algorithm for the fractional set cover.
Maybe from big O, right?
Oh, big O, no. Yeah. Yeah. So this is due to Fritz Heidenbrand, Stefan Funke, Levin Garg, and Johan Koneman. Okay. You can just simply mimic this algorithm for the set cover. So the reason why we get the log n ratio is that it's due to this step. Because row S can be large, but even after you covered this vertex V, you could possibly increase this value xv when you pick other sets containing this vertex V. So you don't increase ys a lot. You just set it to either 0 or 1. But then the xb could be very large. That kind of makes this kind of ratio really big. For the fractional problem, you want something very small. So you need to be very conservative of when we use this, when you increase this value. So, okay. It's algorithm 2. There's a little threshold greater than delta. Now you pick, it's the same, you pick a subset with minimum average cost, and you set ys to be ys plus epsilon. Okay, you just fractionally pick this subset s, and you set xv to be rho s times epsilon divided by 1 plus epsilon. So 1 plus epsilon can be just 1, but you have to increase it by epsilon times rho s. And then you decrease the demand by rho s times epsilon, and actually dv, and epsilon divided 1 plus epsilon. Now you update rho s, and there's a last technical step. So for vertex B with whose demand is smaller or less than or equals to the threshold value, you just set its demand to 0. Okay, and what you do is and you return x bar to be 1 over log n 1 plus epsilon n divided by delta x, and y bar to be 1 over epsilon log 1 plus epsilon 1 over delta y. So you don't have to remember what these values are, but this is very similar to the set cover algorithm with a very conservative update. So this will give you M1 plus epsilon approximate algorithm for the fractional set cover. Okay. Set cover. So to be more precise, you get summation of SC, CS times Y bar S, S0 equals to 1 plus epsilon, summation of B and D, X bar V. So this was the pure objective value. This is for the primal objective value, and then their ratio is less than or equals to 1 plus epsilon. Okay. In time, there are p times n log n divided by epsilon squared. Okay. So Pn is the time. Pn is the time for step 3. Step 1. So I didn't tell you how we pick a set of minimum average cost when there's an exponential list of subsets. But in our case, we had odd cycles, so that's exponential. But you can pick one with a minimum average cost in polynomial time. The Pn there is still polynomial time, although we have an exponential list of odd cycles. Okay. So this is basically it. I mean, I went a little bit technical, but let me conclude using this algorithm, okay, with how we find the maximum cardinality stable set in a T-perfect graph using this algorithm. So so by this, we get x bar b between summation s. So this is an LP feasible value. So you must have LP optimal value lying between these two guys, and LP optimum value was equal to the maximum cardinality of a stable set in G, because our graph was T perfect. Okay, so now I know what this value is, and also this. Okay, if you set epsilon to, let's say, 1 over the size of this vertex set, okay, I know that this value is less than or equals to n, because this approximates the stability number of a graph. Okay, by setting this epsilon to this small number, we know that there's at most one integer lying between these two guys. So you can compute this alpha of G. So that's basically the algorithm. So using this fractional LP solver, you just approximate, you just compute exactly this stability number. Then once you computed the stability number, you can construct the maximum cardinality stable set in your graph G. That's basically the algorithm. Okay. Any question?